This is CCU23 Performance Task Number 11. I am Francis Andescaya from BSC3B. Today I will be reporting about GFDM, or also known as Generalized Frequency Division Multiplexing. So what is GFDM? Generalized Frequency Division Multiplexing, or GFDM, is a block-filtered multi-carrier modulation scheme recently proposed for future wireless communication systems. It generalizes the concept of orthogonal frequency division multiplexing, or OFDM, and features multiple circularly pulse-shaped subsymbols per subcarrier. As a flexible non-orthogonal waveform candidate for 5G, it offers some advantages such as low out-of-band or OOB emission and high spectral efficiency. Here are some of its characteristics. GFDM significantly reduces the requirements set on the analog front end. In particular, GFDM combines both the advantages of specific subcarrier allocation and low PAPR, or peak-to-average power ratio. Low PAPR allows to reduce the hardware cost and power consumption, which is an important point for sale for future wireless systems. Furthermore, each single subcarrier can be modulated individually, which provides a high degree of flexibility in the system design and allows for efficient multi-user scheduling. Compared to conventional multi-carrier systems, it is shown that GFDM is a promising alternative for heavily fragmented spectrums. Here is a figure of a GFDM digital transmitter. GFDM is a multi-carrier system, which digitally implements the classical filter band approach. Cyclic prefix, or CP insertion, is used to allow for low complex equalization at the receiver side. In this figure, you can see that a tail biting technique is used to shorten the cyclic prefix in order to enhance the spectral efficiency. Every subcarrier is modulated individually using some form of QAM signaling. Here is the principle of CP shortening by tail biting. Sharp filter edges are required, which in turn necessitate high TX filter orders. Large filter orders are generally problematic due to the cyclic prefix, which has to be matched to the aggregate filter. Lengths of all system filters involved. However, for the digital TX filter, a tail baiting technique can be applied in order to reduce the CP overhead as depicted in the figure. GFDM used in TV UHF band. Here you can see the opportunistic TVWS allocation for GFDM data carriers in comparison to TV signals. Spectrum holes in the UHF TV bands, or the TV white spaces, or TVWS, are a prominent scenario due to the digital dividend and serve as a motivating use for GFDM. The design of such opportunistic devices is particularly difficult to maintain for two reasons. On one hand, the signal generation should ensure ultra-low out-of-band radiation to strictly avoid harmful interference to legacy TV signals. On the other hand, the receivers should exhibit high sensitivity in order to explore white spaces, um, to sense even very weak TV signals. Apart from these fundamental requirements, there are even more engineering challenges which have to be addressed. Typically, TV white spaces are not consecutively placed in the spectrum. The UHF TV spectrum exhibits strong spectrum fragmentation. In order to efficiently exploit all detected TV white spaces, a system is required in which it can cope with strong spectrum fragmentation and which is able to perform aggregation of several TVWS by one single wideband signal. Hence, the GFDM transceiver is wideband and addresses the following demands: low out-of-band radiation to avoid harmful interference to legacy TV signals, simple equalization despite the wideband nature of the transmit signal, frequency agile white space allocation, and flexible signal bandwidth, digital implementation to reduce the requirements of the analog front end. This is the end of the presentation.